Okay, so let's do this. I'm gonna project a spreadsheet that's blank, which gives us a cheap table, so we could kind of do like the thing that I showed yesterday. And let's do this. I'm gonna ask someone to tell me what the problem was yesterday, like what we studied, the knapsack thing, like what are the parameters. Let's invent a problem, like what's your W, what are the items, and then let's actually just execute it. Again, I just want you to not just get the concept of it, but be able to solve a problem like this. So, anyone, what is the knapsack problem? Trent.
You have a limited amount of space in like a backpack, and you want to maximize the value of the items you're putting in that backpack while also considering the limit of like the weight or space.
Do you remember the variable name?
V and W specifically.
Yeah. I think so. Yeah, I'm erasing right at the same time. So we had basically W, which is your carrying capacity, right? And I think it was 11 for the problem yesterday. We could change that. So what else did you say?
V for the value, or would that be for each item?
So we had a set of items which consisted of pairs of VWs. Okay. So we have a set of items. Each item is defined by a value. This is like, you could imagine this is a dollar value, and a weight, which is how much, if you choose to take it, how much this is reduced. So if you see something and that has a weight of 3, your carrying capacity goes from 11 to 11 minus 3, which is 8. So you can carry less. Did I get that right? Okay. Yeah, and then does anyone remember, is everyone good with this? So how did we do this? How did we solve the problem? Sorry, I have my back towards you, but does anyone? Yeah, Fisher.
You started by creating a table with 2 axes, one being like 0 to the carrying capacity that you have. That was like the kind of the top axis, and then the one on the right was you increased by, or like you chose one item to include, and so you started with no items, and then 1 item, 2 items, 3 items, 4 items, all the way up to the total number of items you have on the left.
So of the 2 dimensions, which one was the weight and which one was the items?
I guess the x axis, or the top label was the weight one.
Is the weight one, yeah.
Yeah.
Okay, this is the next thing. This is the RNA thing, which we'll talk about it at the right time. So let's go to this. I need a bit of a... Come on. Okay, so you said the weight was across. So this is weight of 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. I think that we should actually go with 11 just because, or maybe let's make it the next prime number, 12 and 13. Okay. So depending on what column I'm on, that indicates how much carrying capacity I have or I have left. Okay. And then the items were here, right? Can we come up with 5 items, a set of 5 items? I'm asking you to come up with like basically 5 of these pairs. So does anyone want to propose this? Bridget, you want to do this?
All 5?
As many as you want.
One with a value of 10 and a weight of 4.
Okay, so this is the value column, so 10 and 4, okay. And I will go with a few more if you don't mind. I'm wondering if you have any thoughts about the order of this, whether it's relevant or not. That's something that I actually want us to be able to answer the question, like, is there a significance to the order of this? But so you can give it to me ordered, or you can give me random, it doesn't matter. So we have one item that is worth $10 and it takes 4 units of volume. Do you want to give me a few more?
Worth $20 and weighs 7.
Okay. Don't go more than this because we don't have many of them fit. Yeah. So.
One worth 15
Okay. Good.
and weighs 5.
I was thinking, yeah. So maybe 2 more if you don't mind. That would be the whole set.
One worth 6
Mm-hmm.
and weighs 3.
Okay.
And then one that's worth, say 17 and weighs 6.
6. Okay. Cool. Fisher asked this question, at least one other person asked this question. You don't have an infinite supply of each of these types of things. These are the things, like you literally have 5 objects. You pick up one, there's 4 left. So does anyone remember how we go about doing this? Just want to get this out of the way. Does anyone remember how to do this? Yeah.
Well, shouldn't we give them, like, in a sense, IDs of the subset?
You mean these things, right?
Yeah, but I was also gonna say, like, it doesn't matter how we generated the list, but now giving them the IDs, I feel like we should order them by weight.
So this would be first, that would be
Yeah.
second, that kind of thing. I'm happy to do that, but then I'm going to ask you, did I have to do that? Like, would
I
this?
don't think so, but I think it'll be easier for.
Sure. Yeah. Okay. So that would mean that this is number 1, this is number 2, this is number 3, number 4, and number 5, right? Yeah. And then I think the reason I left this column empty was the first one was. I'm gonna say this.
First one was just empty.
To order to draw the lines, I think we need to have them wider. So if I go. Didn't do that. I thought I could. Why is that? I'll just skip. Okay, so I want to have the top of the problem here. So basically, this is going to answer the question, whatever number there is. And I'm going to assume that this is actually one cell. Whatever number that lives here is going to tell me what subset of these things ultimately maximizes how much money I've taken by the objects. So yesterday, it was the empty set was here, and then it got more populated down. But then I pointed out that that made the top of the problem be at the bottom of the screen. So I'm gonna say this row here, this one right here, is the set of 1, 2, 3, 4, and 5. So in other words, this is when you are on this row right here, your set of considerations is everything. When you're here, your set of considerations is 1, 2, 3, and 4. 1, 2, and 3. 1 and 2. 1. And this is the empty set. Is everyone with me? Okay. I really don't know how to proceed from here on, because if you do bottom up, you actually iteratively populate the bottom row and then you populate the next one. But if you do it recursively but memorize it so that you don't have to do redundant things recalculating, you kind of do function calls. How do you want to do it? Yeah. Sure, and we can do it both ways, but so tell me, down here, that would mean that I have nothing but zeros, right? Okay, So the zero is slightly offline, but okay. Don't worry, you don't have to erase it. I just didn't put them in cells. Okay, so here that would mean that this box right here is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0. Because what chance did I have when I break into a warehouse that's got nothing to steal? Doesn't matter what my carrying capacity is, I can't take anything. Jagrid, take me to the next one.
So for the first one, if that's also 0,
So 0 here,
yes,
and explain.
because like the weight is 3, so you cannot take an item.
Okay, and then so just tell me the next number.
0 till 2, and at 3 you go 6.
Like that?
Yeah.
And then 6 across?
Yeah.
Okay. Oh, 2. Yeah. Next row.
So again 0.
He has a question.
Why did we start like putting 6 when we got to 3?
Say it again.
Why did we start bringing in 6 when we got to 3? Like I know that the value is 6, but why?
Oh, because, so for this first object, number 1, the weight is 3. So until my carrying capacity is high enough, I can't pick up anything. Yeah. Okay.
Why is it still 6 after?
Because at this row, all I consider is the one object.
But I feel like the maximum weight is 13, so couldn't she like take 3 times?
Multiple? No, there's only one copy.
So you can only take 1.
You can only take one.
So you're only filling in the value.
Yeah, that's right, yeah. I mean, this is, again, I said this, but I'll say it again. You don't have arbitrary numbers of these objects. There's only one thing that's value 10, weight of 4. Yeah. So, Jagger, next row.
It will be 0, 0, and at 3 again 6. Then at 4 it will be 10.
You have to do this carefully because I can do this also, but I haven't actually done it for this problem before. So if you make a mistake, like I'm not endorsing it, like kind of have. So why is it 10?
Because like the value of the second item is more than the first item.
So you're saying that when I had a carrying capacity of 4, I could steal this thing. I could take this thing or this thing.
Yeah.
Now I'm going to go with the more expensive one because it actually fits. Now with the remaining carrying capacity of 1, I cannot put this.
Yeah.
So, okay. Good, that's good. So then what else?
10 again,
Mhm.
10 again, then it will be 16.
Mhm. And then all the way across, right? Yeah, so next.
I
Yeah.
have a question. Why couldn't, because I would assume it would have been 16, because after you take the 6, the third one, the first item with a value of 6, and the second one with a value of 10,
Mhm.
then the total value is 16 all through. Why 10 and 5 and 6?
So at this point, my carrying capacity was 3,
Yeah.
and the only thing that I could take was this guy.
Yes.
Okay. So then until it became 4, actually that's the next number. So when I was here, my carrying capacity was 4. This is the part that I want you to explain. Algorithmically, like what made you pick the other one with this? There could have been 3, 4 things. Or if you're at one level, there could be pairs of things being combined, right? So this, in the simple case, as soon as it was 4, he realized that he could now steal the more expensive thing. And then at this point, he had enough capacity to steal both of the things that he had access to. Objects 1 and 2. Objects 1 and 2. So the weight, do you see?
Oh, so you, okay, I
Yeah,
guess.
yeah. Jagrit, next row.
Again 0, 0.
I guess all the way the same, all the way here, right?
Yes.
Okay. 0. Oh, sorry. 0, 0, 0, 6.
6, and then again 10.
Okay.
then 15,
Ooh, okay.
then again 15, I guess. No, 17.
17.
Yes.
We'll have to check this one. So I'll let you finish it, but then we'll check.
And then again 17, yes. And now it's 8. So
Isn't
yeah,
17
then 21.
17 isn't included in the starter block? So it's 1, 2, 3.
It's
Oh
one.
yeah, sorry, my bad. So that'll be like the upper row, not this one. So
Okay.
in this one, it's only the third one, 15. So it'll be 15 all the way. 15, 15, and at 8 it'll be.
Bridget. Yeah.
8,
7, it should be 16.
yeah.
Wait, oh, this should be 16, okay. Excellent. And then 21? And 21 all the way across?
No, 25 max. Oh wait, yeah, 25 max.
Yeah.
16, 21, 25?
Yeah.
And then 25 across?
No.
How 30?
Immediately after?
10 is 30.
At 9, 25. At 10, 25. At 11, 25. At 12, 31.
Shouldn't 10 be 30? Because 15
I am at your mercy here. I was able to do the writing, but not keep track of the numbers. Yeah, Bridget, help me here.
I think that's right.
What's the last number, 31?
Yeah.
Yeah, because there's 3, 4, 5.
So this is, like I said, this is definitely the preferred way to do this, bottom up. Although asymptotically memoized recursion is just as good. And in fact, I'm gonna be able to make that point. I get a little overwhelmed by this, but I think that when I'm doing it the other way, I think this is bothering me. It will feel easier. So what about the next one? Come on, Jagged.
Again 0, 0, 0.
You're the advocate of this. So 0, 0, 0.
6. And again 10. Then I guess again 15. Then 4, 6, 17.
This is 17?
Yes. 17 and now it's again 17 and 8. Again 21, I guess, yeah, 21.
What was that? He's saying, Sebastian's saying that this should be 20.
No, because
No.
5's not in the set yet. But I was
Oh.
thinking, would it be 17 or 16? Because,
The higher number is 17, so it'll be 17. And for the 8th one, it will be 21. And again,
21?
yes. And 25. And then also 25. Yeah. That's no. 27.
27?
Yes.
Okay.
And 27 also.
I think it actually can get higher.
It cannot be lower than this.
Yeah. So 12, 26
That's you.
I have a
Oh,
question.
yeah, go for it.
When you go back to the third one, when you have like 3 items.
Yeah,
This one?
32.
Yes.
It-
And the
No,
item one's
30,
weight is
30,
3,
30,
item 2 is 4, and
Isn't it
item
32, 32,
3 is 5. And the lowest combination
No,
of their
6,
weight
5,
is
3 can
7,
also
which
make
is
up 12.
2 and 1. So I feel like when you, at first when you get the 3, the item's value is 3, which is 6, which is fine, 6. Shouldn't it say 6 until you get to where the weight combination is 7? So 6, 6, until you get to like the 7th row.
Oh God, I got overwhelmed like 10 seconds ago.
No, like my question is, because when we get to, at least in the, what we're putting in is in the value. So at least when we get to 3, that's our weight capacity, right?
Okay, yeah.
Yeah, so we put in the first item whose weight is 3 and now we have, that's why we have a value of 6.
Mhm.
But when you get to 4, the weight capacity is 4, you can't add in another item. So it should stay 6. until you get to.
No, you don't pick the one that you picked in the previous step, you pick the other one, because that's better.
But.
Like
is
if,
it-
so let's say that this is $2, this is $1, and my carrying capacity is 2.
Okay.
So actually, if my carrying capacity is 1, not I said dollars, but like 1, let's say pound, I take this. If my capacity is raised to 2, I take this. If my carrying capacity is raised to 3, I take both.
But from my assumption is the way, at least the way which we're ordering our row is we have a weight capacity of 3, and then 4, and then 5, and then 6, and then 7.
You mean this, right?
Yeah, this
Yeah,
way.
right.
But it doesn't make sense for you to add another item that's weight 4 if.
Can you point to a number that you think is wrong?
Actually, wait. I think I just forgot that the weight capacity was 4. No,
Okay,
I take
okay.
that back.
So Jagged, what about here?
5, 4, 3, 31.
Is that good, Bridget?
From 11 to 13 about what should be 32.
Yeah, it should be 32.
This is 32?
Yeah.
Yeah, because we could do 3 and 4, which is 17, 6, and 5.
I'm really glad the two of you are here. Yeah.
I think the last one can be 30.
Okay.
Oh, yeah.
Cause.
Oh, the last one is here?
I think the last one's 33.
Yeah.
33, okay.
Cause you can do 17 plus 6 plus 10.
So it
You
should
do
be
6, 3, and 4.
32, 31, 33. 32, 31.
No, it cannot go down.
33, yeah, it's 33.
Right, okay.
So it's 33, 33, 33, like 33 3 times?
Yeah.
Okay.
No, 32, 32, 33.
Yeah.
Yeah.
Like this?
Yeah.
Yeah.
Okay. So there might be actually value in finishing this. Like I thought that we would do a few rows and then I could turn into the top-down one. We are only 1 row away. And I don't want others to check out. Like this is, half of you are really engaged, you're getting this more than I do. I don't want the others not to actually pay attention. Let's join forces. Give me the last row. And I'll start it off. That'll be my contribution. I'm done. Now it's you.
10.
10? Okay.
15.
15.
By 13 and 15?
15 and 17.
Okay.
20.
20, so that's the difference, okay? I want confirmation from Julia and Bridget though. Like, you propose, you confirm.
21.
What?
21.
Okay.
Or 9, 56 and 3, so 23.
No, it's still 25.
This is 25?
It's 25.
25, okay, 25.
Pay attention.
It could be 26, but that's not.
27.
27.
3 more numbers.
30 is less than 32.
So it's
32.
yeah.
Okay.
5. 32.
What is it, Bridget?
35.
35? You know how like when something is buffering goes from 0 to 90% and then like just stays there? Like that last number, come on.
37.
37, wow, okay. So we're done. But so, are you clapping my? So let's actually say that there's going to be this. So this just so to make it worth your while. Let's say that we will have this question with a slightly few numbers changed. That's an exam question, final question for a dynamic program, right? You're here, you all did it. There should be a return to that. Is everyone okay with it? Like everyone understood how this is filled?
I have a question. Why couldn't we use like the lower rows? Because when we were calculating it, we were doing it in our head, like making all the different like permutations.
Exactly. I thought that you were doing that. I think that you were doing like a more complicated combinatoric way of doing it in isolation of that row, right?
Yeah.
Yeah, so do you remember how at every point you said like if I'm over here, so we know that if my carrying capacity is 13 and I have access to those 5 objects, the most I could do with subject to that constraint that I have is gonna give me $37, right? So then we said, when you think about the recurrence relation, which is the structure of the way it breaks down, I'll use a different color now. We always had 2 branches. I'll actually use red and green to indicate that green actually indicates I'm taking something, red indicates that I'm not taking that thing, okay? So I would say that the 37 is going to be based on, it's either going to be equal to 33. Like when I didn't have these numbers, I was going to say that I don't know what this number is yet, but I know that it's either going to be equal to this number or me taking the fifth object, which has a weight of 7. So 1, 2, 3, 4, 5, 6, 7. Basically, before, and this is the top-down way of thinking. This is the recursive way of thinking. Memorize it. It is asymptotically as good as the bottom-up one. I'm saying to myself, I don't know what this number is going to be, but either it's going to be the maximum of this number or this number plus the value associated with the fifth object. Right? Now, let's focus on this one. I don't know what this number is going to be, but this number is going to be either equal to this number, which at this point I'm actually admitting that I'm not taking any of the last two objects, or it's going to be, so what's the
weight of the fourth is 6.
I hope, so this was the fifth one, so this from here is the fourth one. What is the fourth? 6?
6.
Okay, so 1, 2, 3, 4, 5, 6. Right, I don't know what this number is going to be, but it's going to be either this number identical or this number plus the value associated with the fourth object going up. So I think that the best way to annotate this is whatever this value plus, so what's the value of the fifth object? 20. I don't want to use blue because it's going to get out of control, but what is it?
20.
20. The answer there, plus 20, or this. Same thing here. Now, the thing is, I only did one. Let's actually do this one. The number here is either going to be equal to that one, which means I'm choosing not to take the object that takes me from here to here, or, so here we're talking about the third object. The third object is
5.
Weight of 5. 1, 2, 3, 4, 5. But so then what's the value of the fifth object? 20, right? No, 15. So it's going to be plus 15 plus $15. Do you see how this is easier to think about? And then at this point also, do you see how a tree is being rendered here? This is the root, left child, right child. The right child has a left child, right child. And the left child will also have, in fact, let me do that one also. This one is going to be either this or the weight of the fourth object, which is 6. 1, 2, 3, 4, 5, 6. So you could see this sort of like skewed tree, but nevertheless it's a binary tree. And the reason why we had to do this upside down, the official slides puts this box at the bottom, which is inverted to the way we explained this. So this box represents what's the most I could pack value-wise if this is my carrying capacity and I have those 5 objects. That answer hinges on what you choose to do with the fifth object. This is the value of not choosing it. This is the value of choosing it, but your carrying capacity is compromised. And so then when you actually kind of like take it out, shake it off, you end up getting this kind of thing. Rows, let's say 5, 4, 3, 2, 1. This is row. So basically R equals 5, W equals 13 has a left child that is R equals 4 and weight equals 6. And it has a right child which is R equals 4 and weight equals 13. Right? And I can do this, it's going to be a tree that's 5 deep, and in all the cases it hits this 0, which is where the recursion stops. Now, when you have a box here with different color or same color but multiple arrows go to it, that's where the recursion suffers. Because you would then recalculate it over and over again for every arrow that corresponds to it. But if you have this table and you actually store that answer as the recursion is collapsing back up, then it's just an O1 lookup. So then I can take this, so you're advocating for the bottom up one. I can come up with like large sets of inputs, various W values, various sets of things. And I would run, like I would literally time your algorithm, the bottom up iterative one. And for the same data set, I would do the memoized top down one. And if I divide the times of the two of them, you get that flat line. So the difference is going to be a constant. So yours and mine will be asymptotically in the same complexity. They could be different by a k. But the reason I prefer this is because I invested all this time to comprehend recursion. Why should I invent another way of actually doing the problem? Yeah. Is everyone okay with this? This is actually quite difficult. Like, you know, if you're getting this is kudos to you, but I just want to make sure that everyone is really getting it. Like, is there anyone with a question?
For the recursive thing, because you start in that top right box in this example, and you would keep moving your way down. Are the like base cases is when it's equal to 0, or is it just the bottom row?
Yeah. I think that you can also consider the first column to be a base case.
Because it would just climb all the way down anyway.
Yeah. Yes.
I have a question on the selecting, so like the ones in the middle, because I'm sort of assuming it's, for example, in the first one you can only have, if there's only one item in the bag, you can only get a value of 6. So for the second one, you only know it's going to be 6 plus. It's if either you take the first item or you take the second item. That was very sense.
I mean, let's actually talk about like now that we covered recursion, where's this 10 coming from? The 10 is coming from saying that it's either going to be equal to that. Now we know that wasn't the case. Or it's going to be like, what's this? You're actually considering the second object. Second object is worth 10. So what was the weight? 4. So look, 1, 2, 3, 4. You're within the table. So the weight fits. So you choose that over the value that was directly under your feet. And this is what he was saying. Like, he was actually solving it combinatorically in his mind. But what Jagger said was, we could have looked at the row underneath it to actually populate it, and that really would have made it simple. But then I exercised that whole thing as I was doing this, which was a little bit more natural to me. Yeah. So again, is everyone okay with this? Like, you could actually solve this problem given another instance? Yeah.
I'm kind of lost about like how where the tree comes in. Like,
The tree was, so I just want you to think that the tree actually is not the product of this. A tree is the way to visualize it. So did you understand how the numbers were calculated?
yeah, I understood how. Yeah.
Okay. You have something?
Well, I was going to say, it also seems like it's an easy way to know which items are actually the ones that were chosen, not just
The tree, you mean, right?
Yeah.
Yes.
Because then you can follow the actual pathways of which, it's like, you know, it was picked and then picked and then, you know, like.
Exactly. In fact, like, I'm going to get back to your question, Jay, but so when you actually look at the way the decisions are made, you either go up a column, that means that that particular object was ignored, or you go like at an inclination, which means that object was taken, so it lets you figure out the precise subset that gives you that maximum optimal value. Yeah. To answer your question, Jay, the tree is a way to visualize the structure of the problem. It's actually not like computational. I'm just saying that this 37, that 37 was the best of the two options you have, which is either this number, and what is that? What does that mean? This means that you're going up without your weight carrying capacity changing. That means that you must not have taken that fifth object because it did not reduce your carrying capacity, or you did choose take it, which means your carrying capacity went from 13 by the amount, the weight of that fifth object.
Okay.
Yeah, and then I applied that to all the nodes.
Okay, and then going down is just the set of objects that doesn't include the fifth one.
Yeah, right. And now you should also be hopefully you're convinced. The order of this doesn't matter. I think that it is for us to do the bookkeeping. It might be helpful to have it ordered, but it doesn't. The algorithm doesn't require that.
Yeah, I think what I'm confused about is like, I understand that, but how would we be doing that without having those values filled in? Like, Like you're saying we could just do it, so like,
So this is actually a subtle point that I'm glad you mentioned. In the bottom-up implementation, you have no choice but to fill it up all the way. In the recursive one, you don't necessarily fill all the box. So yeah, so that actually ends up being a slight positive for the memoized recursive one, yeah. But the thing is, recursion, think about put your Comp 210 hat on. The cost of a recursive call compared to the next iteration of a for loop is way more expensive. So that's why people usually prefer that, even though they're filling some boxes that are not really used, yeah.
oh, so the bottom box is preferred.
Most algorithm textbooks will say that, but my point has always been, if the memoized recursive one makes sense to you, it's not asymptotically worse. To me, that's just as acceptable.
Oh, so whichever one.
Yeah, asymptotically, either one, yeah. Okay, is everyone good? Yeah, like I said, I'm really proud of you. I have not gotten to dynamic programming in previous semesters, and this is actually one of the non-trivial problems, so kudos to you. So tomorrow, we only have 30 minutes left. I just want to show you this. Let's pull this down. Don't die on me, computer. Yeah. Are there any bio majors or minors here? Nobody, okay. Not hearing anything.
Here is a cell, the basic unit of all living tissue. In most human cells, there is a structure called the nucleus. The nucleus contains the genome. In humans, the genome is split between 23 pairs of chromosomes. Each chromosome contains a long strand of DNA, tightly packaged around proteins called histones. Within the DNA are sections called genes. These genes contain the instructions for making proteins. When a gene is switched on, an enzyme called RNA polymerase attaches to the start of the gene. It moves along the DNA, making a strand of messenger RNA out of free bases in the nucleus. The DNA code determines the order in which the free bases are added to the messenger RNA. This process is called transcription. Before the messenger RNA...
Do you see that object, messenger RNA? That actually, the problem will be formulated in terms of that object. And so there's like 4 different symbols. ACTG, I think. It's one different from DNA, like there's 1 letter difference. And so you have 4 things. One thing here couples with 1 thing here, but not the other way. Actually, 1 thing of the 4, like they basically have pairs. Like this goes with this goes with this, no matter where you put them. So there's these couplings they want, and no other coupling exists. So the minimum energy state of this molecule is figuring out the most number of times it can fold and connect back to itself. So let's say that this green and green goes with blue. I can connect this green to this blue. And when I do that, there's going to be kind of like, do you see how there's going to be a lollipop? Like the last one connects to this one, and then you have the stem of the lollipop. You then have the sub-problems. Within that lollipop, can you find other these tips that are merging? And then also within the lollipop, it's going to be like a smaller version of the original problem. Can you actually figure out them? So the question will be, given the affinities of these things, like one color will go with the other color, what will be the alignment for you to connect that thing to itself to maximize the number of connections? And this ends up becoming a 2-dimensional memoization structure that unambiguously is the most complicated dynamic programming question you will see at the undergraduate level. And this is just as complex, no more, no less, than what I said, diff on the command line. Like I'm talking about literally this thing. So cat into 1, 2, 3, 4, or cat into that. So this is going to be 2. So let's say 2, 3, 3, 3, 4, diff 1 and 2. And it tells me that the two text files differ in that line. So this is basically the basics of version control. The dynamic programming solution to coming up with a minimum set of differences so that if applied, one file turns into this other one, they are basically at the same level of difficulty, two-dimensional memoization structure. So tomorrow, we're gonna figure out like how do you calculate the maximum number of ways it can connect to itself, subject to some constraints, like you can't have a connection to its immediate neighbor, kind of like a garden hose that you can't turn it into like a two shot per corner. There's going to be a minimum distance, and then that problem is what we are doing tomorrow. Okay, I would advise you to take a look at that section. It's really well explained. It's really advanced. If you can understand it, it's going to be very satisfying. I really hope that you can actually take a look at it for tomorrow.